Okay, so variation of parameters. So undetermined coefficients is your go-to. If undetermined coefficients works, awesome, use it. It's faster. Variation of parameters is the next thing up the food chain, so to speak. So basically, we're trying to solve something, and I'll use the standard notation. I'm ignoring my other notation for a minute here. ay prime prime plus by prime plus cy equals to g. So this is what you'll see in a lot of differential equations books, this notation. And we're also going to assume you know the fundamental solution set. So you have y1 and y2. And we also know that the Wronskian, right, the Wronskian of y1 and y2, which is equal to y1 y2 prime minus y2 y1 prime, we know that that's not equal to 0. All right. And however, I am not assuming that a, b, and c are constants here, okay? Or am I? No, I'm not. I'm not. So we do assume, so here a, b, c are functions with a not equal to 0. And this is all on some interval of consideration, on some I. So some connected subset of real numbers, I have this data. So what I want to do is find a particular solution through some technique. Now, what did we do? What did we do for constant coefficients, really? We assumed what? We could build a solution from a sum of the things that came from derivatives of g, right? Like so, or if you look at it from the annihilator's perspective, we used a sum of solutions, right, to the corresponding homogeneous problem. So a natural guess to make here would be, maybe we can do something like that here. Maybe in general we can guess that the particular solution looks something like this. So here's our guess. We're going to guess that we can write yp as equal to, say, v1 y1 plus v2 y2, where this v1 and v2 are unknown, yet unknown at least, functions. I mean, if we can determine functions to put there to make this a particular solution, well, perfect, right? So let's make this thing famous. I'm going to call it star. I'm allowed that joke once a day. All right, so there you go. If this is going to work, what do we need? We have to be able to plug that in up here. Now this, again, y1 and y2 are the homogeneous solutions, right? So we still know that, like, a yj prime prime plus b yj prime plus c yj is equal to 0 for j equals 1 and 2, right? That's given. Okay, so we differentiate. Am I in frame, Belu? Okay. Yp prime is, we got product rule, right? So you got v1 prime y1 plus v1 y1 prime plus v2 prime y2 plus v2 y2 prime. And we can rewrite this, all right? So what we have is v1 prime y1 plus v2 prime y2 parentheses plus v1 y1 prime plus v2 y2 prime. So a convenient additional add-on to our guess. I mean, for example, Landon, you might look for a wife, right? And so, like, your first criteria could be she has to be taller than 4 feet. Your second criteria could be that she has to be shorter than 7 feet, right? So you can take a criteria and you can add more criteria. Fair criteria. I mean, can cook spaghetti, enjoys playing Monopoly. I mean, you can get too greedy, right? You can get too greedy. You can put too many criteria on there so there's no solution. It's possible. So you have to be careful not to put too many criteria on your guess that you're trying to, I mean, you have to leave enough flexibility in the guess to make it work, but one very convenient thing we can do at this point, at this juncture, is just say, I'm going to look for V1 and V2 that makes this be 0, because if I do that, well, then at least I don't have to think about second derivatives in V1 and V2, which would be super nice. So we're just going to assume, and this, you can make assumptions. They may or may not turn out to be reasonable. In the genesis of this thought, it could have been that you tried this and it blew up in your face. You were so restrictive in your choice of guesses that you didn't have anything left to work with.
Never find a wife.
Never find a wife. That's right. So depending on who you are, that might be a good thing, but wouldn't be for me. But yp prime prime, as you can see then, is just going to involve this, because the other part's 0 by assumption, right? And so yp prime prime would then be v1 prime, y1 prime, plus v2 prime, y2 prime, and then plus second derivative terms, right? Plus, I did the product rules a little weird here. v1, y1 prime prime, plus v2, y2 prime prime, right? You guys with me? Okay, so then if you go back up in here, so then all I've done so far is take derivatives. Now let's plug it in. So you got a yp prime prime plus b yp prime plus cyp equals to g. And we just plug in the what we just found here. So this gives us a times what? A times v1 prime y1 prime plus v2 prime y2 prime plus v1 y1 prime prime plus v2 y2 prime prime, all right, plus b. And I'll only write down the part of yp prime which is non-zero, which is v1 y1 prime plus v2 y2 prime, right? And then plus yp, which was v1 y1 plus v2 y2, all equals to g. Now, you see what's going on here. We've got this term, which is paired with this one, which is paired with this one. Collectively, these give you what? You can factor a v1 out, and you get a1 y prime prime. You get exactly this. I mean, you get a1 y1 prime prime plus b times y1 prime, v1 prime plus c times y1, but that's assumed to be 0, so those terms drop out. And likewise, for the two, this guy plus that guy, also 0. So what we're left with then is a v1 prime y1 prime plus b, plus v2 prime y2 prime equals to what? Equals to g, right? So returning, now it still remains to see whether or not my guess was too restrictive, right? I mean, Landon might forever be a bachelor, we don't know. Let's see here. It's not possible. So let me rewrite it then. We got v1 prime, I'm going to go back to I think it was 0. We have y1 v1 prime plus y2 v2 prime, and then this guy I can rewrite as y1 prime v1 prime plus y2 prime v2 prime. I assumed that a was non-zero, right? I know a is non-zero. That's an assumption. Aha! Well, this is nothing more than y1, y2, y1 prime, y2 prime times v1 prime, v2 prime equals to 0 and g over a. You should recognize this. This is two equations, two unknowns. We can solve this thing by Cramer's rule. So Cramer's rule By the way, what's the determinant of this? Exactly, it's the Wronskian, yeah. But more specifically, y1, y2 prime, which is what Landon was about to tell me, minus y2, y1 prime, which you'll recognize as the Wronskian of W1 and W2, which we know is not equal to 0 because we're assuming that this is a fundamental solution set. So we are dangerously close to proving the result that if you have a fundamental solution set and if you have a continuous forcing function, there exists a particular solution by this technique. This technique is called variation of parameters. Let me finish it. Here's the finishing blow. I said dv1 dx is equal to, Cramer's rule says you take the determinant of y1, sorry, it's the first one, right? So I got to do the inhomogeneous term here, g over a, and then y2 prime, right, divided by the determinant of the divided by the Wronskian, right? Well, anyway, I'll write it out. Determinant y1, y2, y1 prime, y2 prime. So what's that give us? That gives us minus y2 times g divided by a times y1, y2 prime minus y2, y1 prime. So therefore, v1 is simply the integral of minus y2 g dx over y1, y2 prime minus y2, y1 prime. There's an a down here, right? Likewise, are you getting this, Belu? dv2 dx is the determinant of, let's see here, so we leave the first column alone, y1, y1 prime. The second one gets us the forcing term, 0 and g over a. Downstairs, we still got, I'm going to just write it Wronskian because I'm tired of writing the other thing. And so what you get is y1 times g divided by a times the Wronskian. Right? And then we can integrate both sides, and we get v2 is equal to the integral of y1g divided by a times the Wronskian. Now, a common mistake people make when they don't quite understand what we're doing is they'll like put a box around these and go, look, solutions. Well, these are not the solutions. These are necessary ingredients for making the solution, but do not forget, the solution is it okay? Okay. The solution is back over here. So we take those things we found integrals of, and we put them in here. If you think about this, should those be definite integrals or should they be indefinite integrals? I'm suggesting to you, you can just find an antiderivative that suffices. Depends on what you want. If you add a constant, you're automatically adding like c1y1 plus c2y2, which will pick up the homogeneous solution, right? So if you want to add the homogeneous solution separately, you can do just plain old antiderivatives for v1 and v2, because adding a constant there will just add another copy of your homogeneous solution in over here. But I would like to point out to you that this is completely general. Of course, what is the unpleasantness? Those are integrals, exactly. Okay, with that, let me solve an example. This, by the way, this derivation we did can be generalized to the nth order case. It's more fun there. But everyone should see the second order case worked out. It's important to see it. All right. Oh, I don't know. Keep going back to the bad markers. Eventually I'll learn. So here's an example. Suppose we have y prime prime plus y equals to, what did I say, tangent of x? We could do that. All right, that's it. No more. How about this one? It's really good. So let's see here. Y1, so this gives me what? Lambda squared plus 1 equal to 0. So therefore lambda is plus or minus I. Therefore our solution gives us y1 sine x and y2 cosine x. Dead to me. Well, that was the saddest throw ever. So what's the Wronskian? Yay, this one can live. So it's what, cosine x times, I'm sorry, let me just take a second here. So y1, y2 prime minus y2, y1 prime. So this gives me what? It gives me sine times, oh, I chose poorly. This gives me sine times what? Yeah. Is it too late? I'm going to fix this. This should be 2. This should be 1. Because if I do that, then I get a Wronskian, which is, yes, no. So that gives me cosine squared x plus sine squared x, which is popularly known as 1. Okay. So variation of parameters then, v1 will be the integral. So you got to recognize here we have g equal to tangent x, right? And we've got the coefficient a is just 1. So the variation of parameters formula simplifies to just, let's see here, sine x, right? Minus the sine of x times the tangent of x divided by 1 times dx, all right. So what we got here, what are we looking at? What are we working with here? We've got an integral minus the integral of sine squared x dx over cosine x. I'm going to trade that minus sine squared for a what? Yeah, 1 minus cosine squared x. So I think you distributed the minus already. So that was cosine squared x minus 1 over cosine x dx, which is integral of the innocent looking cosine x minus 1 over cosine, otherwise known as secant of x. And of course, everyone knows that the integral of cosine is sine x. And everyone also knows that that's the natural log of the absolute value of the secant of x plus the tangent of x. Because we just know that. Okay, great. So there's your v1. If you don't know that, sorry. I'm not explaining it here. v2 is what? v2 is the integral. You know, in the minus, people always ask me, where did minus come from? The minus comes from Cramer's rule. It comes from solving the system. It's there. I mean, there's a difference between v1 and v2. That's it. v1's the first one. v2's the second one. That's the difference. Of course, these integrals can flip over if you change the definitions of y1 and y2. Like we face a cosine minus secant integral here for v1. If I changed y1 and y2 the other way around, it would flip these integrals. But the difficulty persists somewhere, no matter what your choice of labeling for the fundamental solution set is. y1 was what? Cosine. So here we have cosine. We've got cosine of x. Hey, I like this one, times tangent x. That's the integral of, yeah, that one's better. So that's just minus cosine of x is your v2. So therefore, my general solution is c1 cosine x plus c2 sine x. There's my homogeneous solution. And then plus y1 times v1, but y1 was cosine plus cosine x times my v1 was what? Sine x minus the natural log of the absolute value of the secant x plus tangent x. And then let's see here, what? Plus sine x times v2, which v2 was what? Minus cosine x. Now something funny happened here, right? You can clean this up. You see part of my variation of parameters formula cancels with the other part. And it tells us, in fact, the solution that we're actually interested in is c1 cosine x plus c2 sine x minus cosine of x times the natural log of the absolute value of secant of x plus tangent of x. And there you go. That is the general solution to this problem. As you can see, we really had no hope of solving this with the method of annihilators because we don't get things like secants and natural logs of secants in the annihilator constant, the undetermined coefficients method, right? So this is a pretty standard example. Sometimes I ask this one. You can put secant there. It's not too bad if you do y prime prime plus y equals secant. Anyway, there's a couple dozen reasonable examples of these things. Okay? Any questions? All right, so I guess at some point or another, there's two things I could go and talk about now. Two directions I'm thinking about talking is, the one is the nth order variation of parameters. I think I'm going to do that. The other issue that we should talk about more before we go on is the issue of what else is out there in terms of finding homogeneous solution sets. Because like this one worked out for us, we could find the homogeneous solution set because it's constant coefficient, right? But the derivation I just did works for variable coefficients, right? So it's interesting to ask the question, what can we do with variable coefficients? How do we find fundamental solution sets for variable coefficients? Can we find fundamental solution sets for variable coefficients? That's kind of the next big arc for this course. So I'm going to deal with the variation parameters in the nth order case before I do that. Although only a very mean person asks more than n equals 2 variation of parameters questions on an in-class test because they're nasty. Yes?
When you say variable coefficient, you mean anything to be like a constant function? It's like general function,
right? Right. I mean, well, we'll, like, for example, what if you had y prime prime plus e to the x y prime plus 3y equals to 0? Could you find a fundamental solution set?
That's what we're trying to determine, right?
We will. Actually, I'm not sure I want to find the answer to that particular question. I think it's unpleasant. But you guys already have the necessary tools, the toolkit to do it. You learned it in Calculus 2. They're called power series. Yep, that's half of it. There's a little bit more we can do algebraically, though, that I'm going to show you. Okay. There's a generalization to the operator method. Well, one thing at a time. So suppose you have an nth order problem. Here's nth order variation parameters. So instead of supposing just v1, y1, v2, y2, you start with a fundamental solution set y1 through yn. Your ansatz then is that you've got a linear combination of these n given homogeneous solutions with n unknown functions, v1 through vn. You differentiate the thing, and like we did before, because we don't want a condition on higher derivatives of v, we're just going to say this guy has got to be 0, right? And then you differentiate again. When you differentiate again, you get terms with like v1 prime, v2 prime, and y1 prime. Then you assume that those have got to be 0. Otherwise, when you go to the next step, you'll get second derivatives in v. So instead of having one extra condition on the wife, we'll have like a bunch of them. And then at the end of it all, we get back to the differential equation when we get to the n minus 1th differential derivative. So like here's a second one. Basically, I'm just going to assume this stuff is 0. Now, like I said, I mean, that may be too much of a demand, but it turns out it's not. And so you keep doing these constraints, eventually get to the last one. And so for the last one, I think here, I end up with first derivatives in v and n minus 1th derivatives in the other thing. But you can solve, plus these terms. You can solve, of course, for these in terms of the rest of the differential equation, because you're assuming that the coefficient is non-zero. And then the same thing happens again from all, when you plug it into the differential equation, you get like n things going to 0 because you know that y1 through yn are solutions to the ODE. Those drop out just like they did in the second order case. And you're just left with this one non-trivial equation in the last row, which relates to the forcing term. So the inhomogeneous term, when you get to the system of equations, has n minus 1 zeros and just one, here it is. Just, yes. Okay, fine. Lovely. There's probably a typo in there. let's not find it. So anyway, modulo sign error, who knows what else in there. If you were really, I'm sure you could find things, Landon. You get this. And then you can solve by Cramer's rule. Pops out. And so what is Cramer's rule based on? Cramer's rule is based on replacing like one of these with that, right? And then you have everything else left over. And so what that is, if you really look at it, you notice the one thing that's non-zero is in the last row. So you have the function out through the n-2 derivatives. So those are like, they're sub-Wronskians in the sense that they're based on n-1 functions, which go to n-2th derivatives. That's what I was talking about, those sub-Wronskians earlier. They're formed from the Laplace expansion. If you think about putting this into one of the rows, you'll just end up with the first n-1 columns, rows, and those. It's something I would ask you to do homework. It's probably worthwhile to do it in homework, but for a test, it's kind of a drag. Here's one. Actually, that's just Cramer's rule, I think, because people haven't seen Cramer's rule sometimes. And so there's the, basically, these sub-Wronskians, the determinant of the matrix with the one column removed, and you divide by the Wronskian, there's your V1 through Vn. So like determinant of S1 in the n equals 2 case was minus G times Y2. The determinant of S2 in the n equals 2 case was just G times Y1. But now they're more complicated in the higher order case. But it's just really Cramer's rule. So you don't have to memorize all these formulas if you understand Cramer's rule. You can work it out from first principles, really. Here's an example. Well, here's actually, I'm just unfolding how it works. Oh, by the way, this also works for n equals 1. I sometimes forget to talk about that. But n equals 1, if you go back, is the linear ODE. We solved it with integrating factor method. Variation of parameters reproduces integrating factor method here. It's very natural. It's like a naught dy dx. So what's the Wronskian? It's just y1. So this, you guess y equals v1 y1. And so v1 would be the integral of f over the Wronskian, which was a naught, which is y1. And you integrate that. That gives you the, let's see here. Let's see here. That times y1, I believe, is the integrating factor. Anyway, you can work that out. It really does reproduce the integrating factor method, which is kind of funny. But this one was what we worked out explicitly today. And then I think I have a token n equals 3 example. Oh, here's the secant x example. This example is just to show you that you can do this for arbitrary functions. So this gives you an integral solution for whatever force. I mean, physically speaking, these differential equations correspond to like springs or RLC circuits or something. And then the forcing function actually is, it could be like a voltage source applied to the circuit, or it could be a force applied to a spring. So if I can solve this for arbitrary f, that's like finding the response of a spring mass system with friction for arbitrary forces applied to it. So it's really interesting that, the physical import of these calculations. But my point is, mathematically, you can solve it for arbitrary f, and you find a solution for any f that you put there, which is kind of cool.
F changes how the function works, basically. Like what F
Yeah, different forces, different responses. Yeah. Exactly. One of the things you might notice from this formula, though, one of the things I would point out to you, this boxed formula, if you took F1 and F2, suppose you had F1 for your force, then you had F2 for your force. If you look at it, the solution would just be the solution from F1 plus the solution for F2. There's a superposition principle. So the response of the system is the sum of the responses for each of the forces. This is this principle of superposition. And then, of course, there's also the homogeneous solution, which is just there. Intuitively speaking, physically speaking, what the homogeneous solution is a so-called transient solution. Here, I'm thinking of x as being time. So I'm being somewhat, what's the word? Careless in my analogy. I mean, when you're dealing with something that has a spring mass system, you'll always get solutions which decay to 0. All right, so if you have, you can prove, and that's one of the homework problems I'll assign you guys, is to show that any of the homogeneous solutions to a physically based, RLC or spring mass problem, as time goes to infinity, those go to 0, or they're bounded at least. It could be pure sines and cosines for the harmonic oscillator. Like the y prime prime plus y corresponds to no friction, mass 1, spring constant 1, if you look at it from a physical perspective. But the point is, any of the solutions you get to like the spring force problem, they all are bounded as time goes to infinity. So that homogeneous solution, either it stays bounded or it goes to 0. And after a while, the only thing you have is the response to the forces that are put on the system, which is a so-called steady state solution. And that steady state solution obeys this principle of superposition, that the response of the system is a sum of the responses. So it's a sum of the responses to each of the forces which are put on it. Yeah. Because these are linear ODEs. If it was a nonlinear, not the case anymore, necessarily. Oh, here's the awfulness. So, yeah, that's a third order ODE with solution set constant, cosine and sine. So it's the one of the most unnasty examples I could think of. But my point to you would be this, is that ODE, well, okay, there is something funny that happens at x equals 0. X equals 0 is a problem spot for that, isn't it? I guess the domain of definition for this ODE is what? The forcing term is x, ln x. What's my domain of definition? Yeah, positive reals, right? So maybe those Soboranskians, no, look at that, cosine. So like take x equals to, for example, 3 pi over 2. You see this is 0, right? But it's definitely not the case that, why is there a 0 there? Oh. The Soboranskian is not that. I'm sorry. Oh, what have I done? I think the Soboranskian I'm thinking about is this. Just these 4. Right? So the Soboranskian is really just cosine. Cosine could be 0 even though 1 and sine x are linearly. They're linearly independent. But can 1 and sine x appear as the fundamental solution set to a differential equation? I would tell you the theory of the Abel's formula and all that suggests no. Because if it could, then it being 0 at one point would force it to be 0 at all points. So if it is the solution set to some differential equation, it's a differential equation with a really weird domain of definition at a minimum.
So it could be, you'd have to define the domain.
Yeah. So what I'm trying to tell you is you can't just take any old set of functions and say, this is a solution set. Saying that a set of functions is a solution set to a differential equation is a somewhat, it's